but we'll wait another minute. The course, you know, it's not start time yet. Okay, I think we can get started here. Where I'm just putting this stuff up in case anybody missed these URLs for these web pages. We have a resource page for the main program. There's now plenty of stuff posted there, not just by me, but also by let's see, Kobe and Daniel. The resource page for this particular module is, here's a direct link. So you can either go straight there or you can get there from the resource page here. I'm posting a new paper, or well, there's a new posting on there today that we'll be talking about for a while. So I apologize for having to cancel out on Monday. And as for today, I'll do the best I can. I am dealing with some non-trivial physical challenges. I may or may not make it through all of the time today. We'll see. But hopefully the math enough of it will get across. So let's see, what else did I want to do here? We should maybe remind ourselves of some things here. Once again, these somewhat strange conventions, at least for now, vector fields have no assumptions on them other than being maps from subsets of Rn into Rn, say. Solutions are just differentiable, not anything else, just differentiable gammas on some kind of interval, satisfying this kind of differential equation, and trajectories are the images of solutions. So that's the language that I'll be using. Let's see, so let me remind you of some notation here, and I've added something. So omega, little omega, is always ranging over non-zero real numbers, in case I forget to say that. F omega is this planar vector field, and truly the easiest way to remember this is that it's complex multiplication by 1 plus I omega, and then regarded as a map in two variables. I'm adding some new notation today, and this is going to be, I'll probably pronounce this spiral omega for lack of anything better. This is, it's easiest to express again in complex notation. It's the image of, it's all the e to the 1 plus I omega t for t and r. It's easy to check to see that this is a maximal trajectory of f omega. And so for those of you who I suggested, you know, doing some exercises with these things, if you look at f omega this way, it's extremely easy to see that this is a trajectory of it, because you can just differentiate and the 1 plus I omega falls out. And it's maximal. That's not too hard to see. I should also mention that basically every maximal trajectory of f omega is just a complex multiple of spiral omega. So this is the log spiral. This is what I mean by the log spiral with, I don't know, what people call it, with angle omega or something like this. And we'll remind ourselves that I'm also using this notation of m sum omega, which is the cyclic multiplicative group right here, but it also happens to be the intersection of spiral omega with the positive real axis. And these are easy things that can be checked. So I'll try not to be, we will need some notation at some point, and hopefully won't need too much more than this, I hope. Let's see, was there anything else here? Oh yeah, let's just remind ourselves of this main classification as I've stated it earlier. Now this is for any expansion of the field of reals. Exactly one of the following holds. None of these cyclic groups are definable. There is one, there's at least one that is, but then no non-trivial trajectories of any of these F sub Q omegas. There's some omega such that all trajectories of F Q omega are definable for all non-zero rational numbers, but no unbounded trajectories, essentially no other trajectories of other F sub taus. And then R defines all trajectories. This one could be restated now using the spiral omega thing. Basically, what this is saying is that some spiral omega is definable, but the only other spiral omegas that are definable are the spiral Q times omega for rational numbers. It's easy to see that these are all the same thing. Let's see. So I think that's all I need to remind ourselves of from previous stuff. So I will stop this and then, okay. Today I'm going to be, as long as we've got this share screen thing, a lot of what I'm going to start off with today refers, the details appear in this here paper, so we see this is proceedings of the AMS from about 10 years ago or whatever. So it's got a long title, Expansions of O-minimal Structures on the Real Field by Trajectories of Linear Vector Fields. So this is, at least the first half of the talk of today's talk is going to, a lot of the details are in this paper. I've put a link because it's no longer clear to me what's publicly available through AMS and what isn't, because I can't, you might have to be logged into a proxy somewhere. So there's a copy of this now posted on my resource page for the course in case anybody wants to see it. There's a lot of details of what I'll be saying are in here. I'll have more to say about that later. And then, okay, now comes the tricky part. Let's see, I need to get to this guy. All right, hang on a second. Okay, you should now be seeing just my open board. Let's see if does this look about right?
Yes.
Okay, good. Little bit of trick that has to be used to get that one. Let's see, now let's hide these meeting controls so they can get out of the way. And undo these guys over here. Okay, so let's try to get started here. Need to adjust my position. So let's let R is going to be, so we'll have O minimal expansion of the real field. I want this to have a field of exponents Q. In other words, the only totally defined real power functions that are there are things with rational exponents. And I also want to say that it's going to define all compact trajectories of linear vector fields. And remember, by linear here, I do mean linear transformations, not affine linear things. Okay, now one thing that would be good to say is that's great to declare such a thing. Do we know that such a thing exists? And the answer, of course, is yes. We know let's recall that this famous structure here, R sub n, defines all compact trajectories of any of all analytic vector fields. So certainly, we'll be using this again later. So certainly of all linear vector fields, and we again know it's well known that R sub n has field of exponents q, and it's so minimal. And this goes back to work of Lau from the 80s, I guess. So yes, so such a thing does exist, and we're going to work with these guys now. Oh, so why am I looking at this? Let's just recall that I at least tried to convince you that this game I want to play of expanding by trajectories of definable vector fields, I had these arguments that, first of all, we should certainly play this over O-minimal structures, because if not, we would get these crazy sloppy sign functions and vector fields that no one would care about. I also gave some arguments as to why we should be looking at not have irrational powers, and why we wanted to already have all compact trajectories of linear vector fields here. And let me just remind you that one of the reasons this one is a little bit on the, it's a reasonable assumption. The thing is, if we have an O-minimal expansion of the field of reals, we can always add all of these compact trajectories of linear vector fields and preserve O-minimality. This is by Pfaffian closure. The problem is we don't know even whether for all we know, exponentiation could possibly be definable then, let alone irrational powers. So we just don't know if the field of exponents q is ever preserved. I've tried to think of what kind of example of a candidate even where this would be a problem. I can't even think of a candidate, but there could be strange O-minimal structures out there, so let's get rid of them. So that's why I'm making all of these assumptions here, and that we do have, in fact, have some structures like that we can deal with. All right, so now my next little piece of data here is I'm going to let capital gamma be a collection of trajectories of linear vector fields. Now, I suppose at this point, I should probably put in here also this word regular, because I gave an argument that we shouldn't look at, the trajectories we look at are the ones that should come up in control theory, not be like ergodic or chaotic in any way. As it turns out, I'm actually not going to need this assumption for what I'm about to write down, because of a nice result of one of my former students, Mike Tikonovich. But we'll leave it in because that's the one, it's the general, we should only look at the vector fields that we really care about anyway. So this is the data that I've got at the moment. And so so here's a result about such a thing. Oh, sorry. Need one more bit of notation here. What did I decide to call it here? All right, why not? Squiggle equal. So we're going to let our squiggle be the expansion of my base structure R by all of the trajectories in this collection. Okay, so this is what we're playing the game now with some particular trajectories. Certainly they are trajectories of definable vector fields, because all linear vector fields are definable in here. Of course, in fact, all polynomial vector fields are as well, which is a little more difficult to deal with. But there we go. Okay, so this is the data that I've got now. And here's what I can tell you about this. So exactly one of the following holds. So this is an amping up of our main classification, if you will, for this special case here. So the first thing, I guess I could say it this way, is that there exists a subfield K of R such that up to interdefinability, by the way, I'm saying here that this R tilde is actually equal to the expansion of R by all of the power functions with exponents in K. Now, of course, so if we think of these x to the R, if we think of these as identify them with their graphs, they are certainly trajectories of linear vector fields. If we look, so for example, e to the x, e to the rx, for x bigger than 0, if we differentiate this thing, we certainly see that we're going to get this as a trajectory of it after reparametrizing. So this is one possibility. Another possibility is that we just add exponentiation. Another possibility is that we add log spirals. There's an omega such that this guy is equal to R, and it's tricky to draw there. All right, and again, we know this is a trajectory of a linear vector field. And then finally, the nasty one is just that we define the integers, and so because we're dealing with everything Borel here, actually I might as well just say it this way. It's the reals with the predicate for the integers. So these are the only possibilities if we expand by collections of trajectories of linear vector fields. So let me just explain a little bit of the proof of this is mostly pretty easy. So in other words, showing that these four are possible is actually, it's in the paper I mentioned earlier. I not to belittle the paper, but it's truly just some undergraduate basic Ode theory combined with basic definability theory. At the time I wrote the paper, I didn't have a student that I could have, any reasonably good student could have written the paper, but I didn't have one at the moment I could give it to, so I wrote it. This is not difficult at all. You just have to roll up your sleeves and go through and use the fundamental theorem of linear systems, put things in Jordan normal form, and just check all the possibilities. So getting these four as possibilities is actually pretty easy, modulo checking details. Why are they the only four? That's where something gets interesting, because there's a fifth possibility here, namely that I would have two of these guys. I might have, or finitely many or whatever, that I would have at least two log spirals that weren't just rational power images of each other. That's also a visible possibility in the analysis here. And that is where I use this result of Hieronymy. If I have two different log spirals, I certainly have two different cyclic multiplicative groups, and so then the integers are definable. So that's the hammer that needs to be used in here. This is a combination of undergraduate Ode theory, basic definability theory, and then Phillips' result that you can't have two of these things, two different ones, without defining the integers. So this is what I guess I would call a tameness theorem, or a theorem of tameness theory, if you like, something like that. It says that if we're not in the worst possible case, in which case we know, and we understand this in this sort of nihilistic fashion, that if we wind up defining the integers, then we know we've lost all, we have no way of saying anything relative to what we started with. So at least we know to give up on that one. But what we have here is that if we don't have this horrible situation, then we have a complete classification of things that can show up. So that's the tameness part of it, we could say.
Chris, can I ask, in what sense is option number 3 tame? Maybe you mentioned it in previous classes, but
I actually, I'm going to get to that one. You're right, I have to explain why this one's tame, that's for sure. Okay, so for the moment, take my word for it that this is a tame structure, because I'm gonna have to explain that some more. So that's a good question. But so now you could say, okay, so where is the control theory ever coming into this? Because people have been asking me this. So my answer to that at the moment is simply this. I got interested in this subject called continuous control theory. You start certainly no one can argue that some of the most fundamental objects there are reasonable trajectories of reasonable vector fields. So I am using that subject, this subject called continuous control theory, to suggest to me game pieces for playing the game, or instances of the game. I could have started with anything, but I'm playing the game now with collections of trajectories of reasonable vector fields, and linear vector fields are certainly reasonable. Yes, I could hold out some hope that in the end, this might turn out to be useful in applied mathematics or something, but that is not my concern at the moment. My concern is, why am I looking at things besides just for my personal enjoyment? And so the tameness part is just the classification here. At the moment, the control theory part is simply that was my inspiration for playing the game with these particular pieces. Now, to get back to the point that Kobe was making, the usefulness of the result now and the potential for applications in control theory begins to come this way. We understand exactly how, we understand very well what the definable sets are here relative to here. This is some fairly old technology now, but because we have all compact trajectories of linear vector fields were there to begin with, we have all restrictions of real powers to compact intervals. Once we know that, the technology has been around for quite a while of adding the rest of a real power function and controlling the outcome. So in particular, we know in this case, we're still polynomially bounded. Field of exponents exactly what we think we should have, actually. Actually, I suppose there could be, oh, that's right. This had field of exponents Q. So we know that the only powers there are going to be these from K. Now, to say to write down exactly how much we understand this one in terms of this one actually takes a bit of work. But what I can tell you is something very suggestive, is that every definable function in here is given piecewise by compositions of functions definable in the base structure and these real power functions, although there is a caveat here. If I'm regarding these as functions in the logical sense, we have to put xr equals 0. We have to make it totally defined in order for that to be the interpretation of a function symbol. So the easiest way to do this is we usually just slam it down to 0 if x is less than or equal to 0. So I agree that this notation is ambiguous. On the one hand, we want to think about it as the trajectories, in which case they would have to be binary predicates. If we want to think about them as functions in the logical sense, they have to be totally defined. So we do it this way. The introduction of this discontinuity at 0 does cause some trouble if you want to do a fine analysis of these compositions of things. But anyone who has played around with R sub n or R sub n x or any of these other things, we all know the same thing happens with R sub n, because these restricted analytic functions are set equal to 0 everywhere off their domain, off some compact cube. So there's discontinuities all over the place, and you often have to work to figure out how to get around that. But we really, this is a case where we really understand what's going on with this structure in terms of what we started with and just these guys. Now, something similar here happens. Again, of course, we're still O minimal. Here, we're also going to be O minimal. And in this case, what we have to do in order to explain, let's see. So let's go ahead and throw in log as an extra primitive function here. Of course, that's definable in here. And again, the usual game is if we have to set this equal to 0 for less than or equal to 0. So in this case, again, it's going to be the same thing, that every definable function here is going to be given piecewise by functions definable here, compositions of functions definable here, and e to the x and log, again, with this proviso that log equals 0 on minus infinity 0. So this is convention is followed standardly with like in RNX blog and all these things. I should also, for the logicians here, I should also say that that in this case, this is explicitly admits quantifier elimination and is universally axiomatizable over this one relative to here. There's a relative QE and universal axiomatization. Same here, just like with Rn, X, and log. So not only in these cases, not only we have the tameness result, but then we also have model theory tells us that we actually understand these outcomes extremely well in terms of what we started with. And that was our goal. Remember, the game was, can we understand the expansion by trajectories of definable vector fields in terms of what we started with? So that was the way I stated the game. So in these cases, we're in pretty good shape. Although again, depending on how much how detailed information you want, you still have to do, you're still going to have to do a lot of work here to unpack, say, these compositions of terms because of these various discontinuities that are introduced. But still, it's definitely good information. Now, okay, so now to get back to this one, there's an omega such that that we're interdefinable with the expansion of my original structure just by one of the log spirals. Now, what I'm also, let me add here then that this is also interdefinable with the M sub omega that goes with this. And the reason for this was again tied to this exercise that I suggested. In this case, because we have all, once you have a compact piece of a log spiral, sorry, be careful here, a non-trivial arc, let's say a non-trivial arc of this guy. If you have a non-trivial arc of this and the intersection with the positive real axis, it's a multiplicative subgroup of non-zero complex numbers. So you can reconstruct the entire log spiral from this group, the intersection with the positive real axis, and any non-trivial arc. So now the reason why I put it this way is because, again, we have some technology that's been known for a long time now. By generalizing Van den Dries Laus proof for the case that this would simply be the field of reals itself, we can actually say, because we know this has field of exponents q and we're all minimal, this is well understood also. It's harder to say how much better it's understood, but one of the things that's true here is that every unary definable function is the union of a definable open set and finitely many definable discrete sets. And that's actually true in any elementarily equivalent structure. So you get a uniform bound on these number of discrete sets that might show up as you vary parameters in a definable family. At some point, I gave this the name D minimal because I had to give a name for this property to something. But again, we actually know also a lot more here. There's a routine trick that, again, this is and goes back to Lau's original proof. It's very easy to see that once you have this set here, you cannot have quantifier elimination, simply because if you will, the greatest integer function for this guy is going to be definable, and it's pretty easy to see that it's not quantifier free definable. So if we replace this group with a step function that corresponds to it, it's like the greatest integer thing. Well, you have to make your decision, I guess, and do it there and so on. And we again set this equal to 0 for everything less than or equal to 0. Then if we use the step function, and that's certainly interdefinable with the group, then again, we get explicit universal axiomatization and quantifier elimination of this structure relative to this one. And once again, and then we get the situation where if I have any definable function in here, in any number of variables, it's going to be given, well, piecewise. Be careful what we mean by that, of course. Piecewise by compositions of functions definable in my downstairs O minimal structure and this unfortunate step function. if you roll your sleeves up enough, what this, in the end, what this gives us for this structure, is a, instead of ordinary cell decomposition, we get a countable cell decomposition theorem. But one where where you have these, you might have countable cells showing up, something like this above here, but these functions that show up here, the boundaries of these cells or whatever, these are going to be uniformly definable in a certain way depending on this group. I don't want to go, what I'm trying to suggest is that, yes, this is well behaved. This is still very well behaved relative to what we started with. It just takes a little work to actually explain how well behaved it is. And I don't really want to go too much into that at the moment. There's a decomposition into finitely many definable submanifolds, as long as you don't, but not connected submanifolds. And those have some nice properties. And then they are further refined by these countable cell decompositions. So in all three of these cases, we actually understand the outcome extremely well relative to what we started with. And in the horrible case, we also understand the outcome relatively well, namely that we have no hope of having any connection any further. So we can move on. It does occur to me that there is actually there is a kind of an easy way for me to give a description of definable sets in here that is suggestive that and that maybe I can do. I should do this. Okay, so let's make myself a little more room. Let's see. So this is a weaker result than what I actually know, but this is one that's fairly easily stated, and I think is pretty suggestive. So let's see. If let's say X in Rn is definable in here, in this case, I'm going to stop trying to draw those things there. I'm not doing a very good job in it. Then what do we have? So there exists some, let's say, M in N and Y in Rn cross Rn, definable downstairs. Such that I better leave myself some room here for the, so X is equal to the union over all, okay, let's say P in M omega M of the fibers, Y of P. Sorry here, so Y of P is going to be well, I guess it's going to be the X's in Rn such that P comma X is in Y. So this illustrates, so what I'm saying here is that if you have a set definable in here, it's going to be the union of a family of fibers. There's going to be a definable set from the downstairs structure where we just fiber up into it, controlled by some Cartesian power of this multiplicative group here and take the union of these things. And this is what these things look like. So this is an easier description. So
Do
what
you need to allow definable subset of the group?
Absolutely. And yes, absolutely. In fact, that would be, yes, this, I could have also, in fact, I could start splitting this up. For example, I could say, well, let's look at the P's such that YP is something or other. So in fact, an important property here that's actually not obvious is that the induced structure in here on M sub omega is just M sub omega. And sorry, is just the induced structure on here is just, let's call it multiplicative Pressburger. So if we can think of this is a multiplicative group, so we can think of it as an exponential image of the additive group, and the the subsets of M sub omega to the M that are definable in here are like exponential images of Pressburger sets. And yes, you can split this up and do a lot of things. And in fact, this is, if we rearrange the order in which we did this, this is basically saying that I have a particularly strong form of model completeness of this structure, relative model completeness of this structure. So turn things around, and what am I saying? I'm saying there exists a P in this Cartesian power of the group, so that some formula downstairs holds when you substitute in the parameters. In some of the literature, that would be called a special set, and many of us are familiar with theorems where we wind up getting that things are Boolean combinations of special sets. But in this case, every definable set is special under that definition, plain out. So I think an interesting thing to do here for someone, it's a challenge, if you will. So everything I know about this structure right here, I know because of model theory. The proof uses a saturated embedding test. It uses, allows so-called the Wilke inequality. I don't know a standard proof of what I'm talking about here. I only know a model theoretic proof. And again, that's what this step function introduced here and everything. I don't know how to prove this any other way. I think might be interesting to just simply view this as, okay, this is this sort of strong model completeness result, and just show that the complement of something like this is again of this form. Can this be done directly in the standard model? I think that might be an interesting exercise for someone. And there, Kobe's question would become, I think, quite relevant, is that you actually can let this be, you could actually let this be unions of definable subsets of this guy, which would be Pressburger sets. And so there might be a good classification theorem here that would allow a proof to go through in the standard case. I mean, I suppose that's of somewhat esoteric interest to people who would rather have standard proofs of things than model theoretic proofs. I'm one of those occasionally, but sometimes I only know how to prove things using model theory. If I can see how to provide standard proofs, I often will, but sometimes I just can't. And this is one of those cases. Now, I could make all of this much more coherent for anybody who really wanted to tackle this, say a graduate student or someone. My sincere hope is that I would be physically able to be in fields next Monday. And thereafter, I hope. But anyone who's interested in this as a project or something, just let me know. We can Zoom or whatever. I can make all of this much more precise and get someone started on it if they would want to do it. So just to repeat this then again. So here is a proof of concept, if you will, or here's a beautiful example of the game being played successfully. We're starting with these base structures that we've agreed that we're going to start with. We have some collection of trajectories of interest of some interesting definable vector fields. And we're really able to classify the possible outcomes of what these expansions look like. Moreover, we are then able to use model theory to answer this question of what do these expansions look like relative to what we started with. Always allowing for this the horrible outcome here, which we all agree we have to give up on. So now most of the, as I said, the ODE theory here is really very basic. So the tameness part of it is well understood relative to Phillips' theorem. And then all this model theory stuff I've been putting out, these results have been known for a long time, although perhaps the business about expanding by the cyclic groups isn't known as well as it should be. Could be partially my fault, I think. But so at least we have a motivating example of successfully playing this game. It's certainly been one that's been motivating me for years, and this is kind of my idea of how to play how we want to play this game. Now you might say, well, why should I use control theory? Why should we even think about trajectories of vector fields? Why don't we think about other things like I don't know, special kinds of functions and all these other things? And yes, you can certainly play the game that way as well. And there's something to be said there. But this is the one I want to play right now. So let's pause and catch our breath here for a minute before I move on a little bit. Does anybody have any questions or comments that they'd like to make about at this stage of the game? Okay, so there's a few other things I want to add here, because these are all fun things. Now, actually, I guess I should come back here. Here's our R. Let's go back and look at this assumption here. So an O minimal expansion of this field of exponents Q defines all compact trajectories of linear vector fields. Abstractly, there has to be a smallest such thing. We already know that it has all these nice properties here because it's evidently a reduct of R sub n, and we already know all these nice properties hold there. So we could have what's interesting for me is that in fact the smallest such thing is well describable, and in fact has popped up in the literature before. So I'm I'm very happy when these kinds of things happen. So let me say a little bit about this. So what is the smallest such R? Or is there a better way to describe it? And in fact, there is. So we can basically say it's the field of reals together with restricted exponentiation and restricted sign. And I'm using, this is the original, let's see, so this was called something like, I don't know, RRE or something. Many of you will recognize this from work of Van Andries from published in '88, as I recall. The RE here stands for restricted elementary, and this has a very nice model theory, and this led to consideration of convergent Weierstrass systems and so on. And the reason why this is the smallest such structure, of course, once we have sine restricted to here, we also have cosine. We also have e to the x on any compact interval just by the homomorphism property. Similarly, we'll have sines and cosines on any compact interval, any given compact interval, by the addition formulas. And it's known that so all coordinate functions here of solutions, we're going to say of solutions of linear vector fields. So I've got a gamma now, and I'm looking at it. Are let's see, basically linear combinations of things like, let's see, so it's like, say, t to the k, e to the at, and then either cosine bt or sine of bt. So this is after you bust things up into, anytime you get a solution of a linear vector field, you're going to wind up having a linear combination of these things. K here is an integer, and A and B are real. And this is simply a corollary of the fundamental theorem of linear systems, that this is what things look like. And so we can see visibly now, if I have on any compact box, well, for t in any compact interval, certainly the restriction of this to the compact interval is going to be definable in here. So in this case, not only are all of the compact trajectories of linear vector fields definable in here, in fact, all of the solutions on compact intervals are in fact definable. So I personally find it gratifying that we invent this thing and we say, okay, well, for various reasons, I want to look at the smallest expansion of the field of reals that defines all compact trajectories of linear vector fields. And it happens to be another structure that's of interest and has been studied. Well studied, I should say. In fact, let's see, somebody here probably will remember this better than I do. This also came up in some of this point counting business. I think Gal and Dimitri, or some of the gang did some things with this as well. I can't remember the outcome of it. So it's a very nice structure, comes up in different ways, and it's nice to know about this. Okay. So, are there any questions or comments at this point? Okay. Believe it or not, I'm flying blind at the moment on the time. Does anybody know what time it is?
It's 10:05.
10:05. Okay. I would like to suggest that we take a 5-minute break.
Sure.
I know I need one. So I'll pause here and I'll be back in 5 minutes.
Sure.
I pause the recording.
Oh, okay. Do we get another, like, when you resume a recording, do we have to watch out for that button again, or?
A priori, no. For me, it's ongoing, the recording.
Okay. All right.
Thank you.
All right. So yes, I was very confident that I could get through the first hour. Now I'm starting to stiffen up a bit. Now we'll have to see what happens. But okay. So we've got this motivating model for the process here. And so what's next? Well, okay, there's different directions we could go in this. But one of the first things I need to remind ourselves of is that in order for us to get that nice little result, depended very strongly on having a lot of knowledge of the ODE theory. We really understand trajectories of linear vector fields extremely well. And even, again, this is just some nice undergraduate mathematics. This begins to change as soon as we even go to polynomial vector fields. I'm sure many people in the audience know that even when you start to, even you can easily ask questions about trajectories of polynomial vector fields or so on, that can get you into trouble. So what's so where is our next move here? So we're going to try to ape, basically. First of all, let's go ahead and let's just say for concreteness, we're going to take our base structure to be the famous R sub n. That certainly fits the bill. All trajectories of linear vector fields there, and in fact, all compact trajectories of analytic vector fields are definable. So we don't have to worry about these at all. And that means real analytic, of course. All right, so now we already know what happens if we're adding trajectories of linear vector fields. We get these outcomes that we had before. So you might think that the next natural step would be to try to deal with trajectories of polynomial vector fields, but in fact, the development in ODE theory, and now that we're in this setting here anyway, is it's more natural to start looking at trajectories of analytic vector fields near singular points. So this is, I mean, I can't prove this statement. It's just one of these things, but in ODE theory, the next step after linear, next step tends to be looking at analytic vector fields. Well, in fact, let's be precise, analytic vector fields in the plane. That'll make it easy. In the plane, near isolated singularities. So zeros, isolated zeros, or places where it's not defined. Oh, that's ugly. Well, singularities. All right, so that's kind of what we're going to do as well, and see what we can where we can get with this. So I guess sort of the picture here is, you know, we will normalize something. We'll have this vector field, and we'll normalize it so that we're vanishing at the origin. We're going to look nearby at what happens, and you know, okay, so we've got, you know, some vector field here doing things, and it's going to be an analytic vector field. And the game is really to try, because globally, once we get away from the singularity, if we have a trajectory of this vector field that doesn't go near the singularity, or any other, I should say, singularities, well, okay, any compact piece of it is already, it's already definable, and it's not causing any trouble. So the main thing here is, you know, what's going to be the behavior near singular points where we don't have compact trajectories. So this is usually the next step when you're trying to develop the ODE theory. So we're going to do this as well. And the general approach there also is to say, okay, if my analytic vector field will have, say, I look at the power series expansion of it. It's, again, it's two variables into two variables. If its linear part is non-zero, then we can hope that the trajectories are behaving enough like the planar linear vector field to be able to analyze things. And so this is the next step in the game. And of course, on the other hand, if your linear part is zero, well, then your trajectories are probably not going to be much like the zero vector field. And you have to start doing things like resolution of singularities, or putting things in normal form, and so on, like that. So this is this is where the ODE theory knowledge is. So that's what we have to chase, at least for now. But we also have some extra ammo in the game now. So remember, at the outset, we hope to get rid of trajectories that we just know are going to define the integers. And one of the ways we can do that now, using this stuff that Philip and I developed, is to show that that the Asawad dimension, or if you don't like Asawad dimension, just let's think of any of the ones you like, box dimension, anything like this. Even Hausdorff dimension is okay in some cases. So we are going to be able to use, we're going to be able to use some of these tools to simply look at certain kinds of trajectories and know that they're no good. They have to go. And then another important piece of technology here, that a big box that we're going to have to be using is this Pfaffian closure machinery, due to Patrick. In this generality, it's due to Patrick. This is a big hammer that we're going to have to be using. I'll be explaining just when I use it and how it's being used. But I will at this point like to make an advertisement. If you really want to see a proof of Pfaffian closure, well, of course you can go to the original paper. But in fact, there is a chapter in the Fields volume from our 2009 program devoted to this theorem and its proof. And so on my resource page, I strongly recommended that there's a number of really good things in those lecture notes. And this is certainly one of them. So we're gonna have to be taking this as a black box in order to get further with this. That's all I can want to say about it right now. So what would be an example? So let's say a motivating example for where we might go here. So let's say, let's suppose we have we have some nice analytic vector field. F, we'll call it F1, F2, I suppose, in case we need it. This is analytic vector field at the origin. And let's just say that's the only isolated. Let's just say it's an isolated singularity. This is what we reduce to this anyway. Now, a very special case of this is, let's also consider the case that F, my F, is actually equal to one of my F omegas plus higher order terms. So what I'm saying here is that if I write out the power series expansion for F, which is again 2, if we write that out at the origin and suppose that the linear part, the first part of it, that it actually starts off with one of our F omegas. Now, we know what the behavior of this is very well near the origin. The trajectories of here are, the ones that go to the origin are pieces of log spirals that are going down to the origin, or complex multiples thereof. So we would hope basically that we can play on this to say basically that if I would really like to say that adding any of those trajectories that are spiraling towards the origin is going to be the same as adding the spiral omega. So that in fact, we still get one of the same outcomes that we had before. Let's see, can I draw? So in this case, we know that the F omega is being some nice log spiral here. Oops, okay, best I can do. This is coming from here, so we've got an S omega here. And the question is, how much does a trajectory of F now look like compared to this? So now here we get to use some Ode theory, and it turns out that this actually works out really well. So in this case, now let's say gamma be a trajectory of F that's going to the origin. I'm going to have to start drawing pictures because this stuff gets pretty that goes to the origin. Or let's say the origin is a frontier point. Okay, so then in fact, we will again have R sub n expanded by this is going to be interdefinable with R sub n, the spiral omega. So now why is this true? There's a couple of ways to see this, but the famous sort of ODE way is because it's known that when you have an analytic vector field like this, and say an F omega as its linear part, that there actually is a real analytic diffeomorphism in a neighborhood of the origin that takes the trajectory, this gamma, at least that once I get close enough to the origin, this can actually be straightened out, well, straightened. This can actually be rectified and turned into a trajectory of actually S omega itself. And this is done with an analytic transformation of the neighborhood of zero. So that's a compact thing if you look at it close enough. And so it's definable in R sub n. So in R sub n, I can take this trajectory and literally transform it into a trajectory of, into an arm, into a trajectory of the log spiral. And so what's going on here? And then they would be interdefinable.
But you do it locally or globally?
Locally.
The diffeomorphism.
It's local, but of course, once you know S omega for near the origin, it's a multiplicative group. You can, then you make it also out to infinity, and then the compact pieces are all there anyway.
Right. Thanks. Yeah.
Right. But yes, it's a local, it's a germ, you think of it as a germ transformation. But now how does that proof go? Where does this analytic thing come from? Well, I might be getting a little out of my depth here, but so there's the notion of formally transforming the power series here into this linear part, and this is I'm having a moment here. Watch out. So I think this formal transformation goes back to Poincaré or something. And at some point, someone proved that as long as you start with an analytic, as opposed to, so in other words, even if it's C infinity, there's a way of transforming, formally taking F and transforming it to its linear part. Now the question is whether that actually is a convergent, whether that actually is a function or not, or does it only work formally? If you're starting with an analytic one, then yes, it actually, this formal transformation is in fact convergent and analytic. And this is a theorem in Ode theory, and this one, I don't know if you would call this undergraduate, but it's certainly not as common as some of the other ones. But this does work. So we know that over R sub n, at least, if we even have a trajectory of something whose linear part is one of these F omegas, then to all intents and purposes, we're still just dealing with the log expansion by a log spiral. So that's some oh, something's happening here. Okay. I occasionally get surprised by this piece of software. Now, you might say, well, what if I didn't have R sub n there? What if I didn't actually have this transformation right there? well, that's fine. Okay, maybe we can't actually say that we can define the S omega, the spiral itself. Maybe we can, maybe we can't, but at the very least, so in other words, if I'm just looking at my original, say, arbitrary script R that's polynomially bound, or that's O minimal field of exponents Q and so on. If I try to add the gamma to that, will I always be able to recover definably recover the log spiral? I don't know. I don't know for sure. But what we do know for sure is that in this case, if it were a reduct of R sub n, then I know that I can find a bigger O minimal structure that also has field of exponents Q and is O minimal and defines all compact trajectories of linear vector fields, where I would get this classification result that I want. So eventually we have to build in the idea that we might have to occasionally go to bigger structures than what we started with in order to actually get everything we want. But hopefully we can do that in a way that preserves O minimality and field of exponents Q. So there's a big area right there where there are things we don't know. But this actually this would be one of the nicer cases. So let's go ahead and not worry about this one for the moment. Just say, okay, at least in one of the most important cases that we care about, namely log spirals, if I look enough like one, then I'm basically going to be enough like it so that I can define it possibly in a slightly larger structure. Now I have to try to figure out what this is doing. It's decided that it doesn't want to go down anymore. All right. Well, I guess we'll go over for a while then. I just discovered that limitation. Now, so then there's some other there's lots of other results about analytic vector fields in the plane near isolated singularities where you can sort of play these same games, where if you know enough about the linear part, then you can say that that your trajectories, your phase portrait will look enough like that of the linear part so that you can really get somewhere with it. Beyond that, there are problems, and it does start to break down for a little bit. And this is one of the areas where we have to work at things. But let's consider another fact that's simply known about these things. So here we go. I have again, we'll stick this page. I have an analytic vector field on 0 at the origin. That's the only 0 nearby. So here's my F near the origin. I'll go ahead and just say R squared, although we're really thinking close to the origin. Analytic. So another theorem that comes out of this classical theory of such things is that one of two things happens here. In some books, in fact, I think this is called, I think Arnold called this the fundamental dichotomy or something, or the fundamental, yeah, something like this. I can't remember the word, fundamental dichotomy or something. Oh, alternative, that's what it was, the fundamental alternative. So basically, only two things can happen qualitatively in this setting. Number one, you have a spiral. You have some kind of spiral that has to come into the origin. Now, okay, yes, we have to do some work to make exactly what spiraling means and these other things, but that's not too hard to do. That's one possibility. The other possibility is that there has to be at least one trajectory that comes in and behaves itself very nicely. In other words, there has to be a limiting tangent as you come in. So either you spiral like this, somehow like this, or you have to have a trajectory that comes into the origin in a more or less controlled and straight way. And so, of course, if you if you have any trajectory that does this, then you certainly can't spiral. So there's your any other trajectories that do manage to come to the origin are also going to have to be, you know, kind of have this look to them. And this is proved by just, you know, it's Ode theory, plain and simple. So so this is a key fact about analytic planar vector fields. Well, fortunately for us, this is basically okay. This is, we're just basically say this is true just from the O minimality, we'll say. Okay, so what do I mean by that is that if instead of assuming analytic here, we really were just saying that we have, well, let's just say C1 or C2 or something like this, some nice enough conditions on our vector field near the origin, and this exact same dichotomy is going to hold. Either we spiral in which case all the trajectories have to spiral in some neighborhood, or we wind up getting we wind up getting a picture somewhat like this. And in this case, it turns out that each one of these trajectories is in fact definable in the original O minimal structure. So here we have, what we get is something that's either evidently not O minimal anywhere near the origin, or we get a situation where every trajectory that's near the origin winds up being something from the downstairs O minimal structure. Oh, sorry, no, that's not true. Winds up, sorry, it's definable in the Pfaffian closure. If you add these guys, you'll preserve O minimality. And so that part, getting this dichotomy here, or this alternative, is really just it's a question of looking at the proof in the analytic case and looking at it very carefully and using O minimal ideas to get rid of some of the stuff there, and you get this nice split between behaviors. There's a complete proof of this in some ancient preprint, or not even preprint, I wouldn't call it. There's a note that's posted on my webpage that Patrick and I were writing. It's way out of date now, but there's a proof there of this that's pretty straightforward. I believe there's also a proof in the 2009 lecture notes from the program, then in the chapter by, I think it's in Fernando's chapter. Anyway, so in any case, you can see complete details of this. They're actually not that difficult. So what this tells us is that if we're dealing with, we can stick with the analytic ones, but in fact, if we're just dealing with nice enough O minimal vector fields, and they're pretty basic, we know that we can either boil down to where we can add all the trajectories and they live in a single O minimal structure, although possibly larger, or we wind up with something that looks like this. Now, it's possible, this is the reason why this is the kind of picture now. There's two things we should think about when we see this picture. One is the so-called Poincaré, the return map. We might as well take it along the positive axis. We know that, you know, you cross this and you'll have to come around and you'll hit it the first time, and again, you'll hit it another time, and you'll hit it another time, and so on. So the intersection of this abstract spiral with the positive reals will be some kind of sequence that goes down to the origin. If this looks enough like one of the M omegas, then in fact, you can define the M omega from it. And then the spiral omega that goes along with it, and then you'd face the possibility of how does this thing compare to the spiral that you think it's supposed to look like. So these are issues that need to be that can be worked on. The other thing is that if it doesn't, there are so-called slow spirals that can show up, where you're not actually coming down in an exponential rate. This is actually coming slower. In that case, you can actually prove that you can do this either way. Either the Asawad dimension of the intersection with the positive axis is positive, not zero, in which case we define the integers, end of story. Or in most of these, if you have one of these slow spirals, you can usually actually even, you can just computationally check that the Asawad dimension will be greater than 1. And because it's going too slow, it's, you know, if things are taking too long to pile up, then you wind up getting too much concentration of one-dimensional stuff, and that's what Asawad dimension checks for. And so with these spirals, the tendency is that either you look enough like a log spiral so that you don't cause trouble, or you look enough like a slow spiral so that you're back in the integer case. All of this leading to, you know, a conjecture of some sort that if you have a spiral here, then, and you don't define the integers, then the hope is that you would be interdefinable with a log spiral. But some of these things are still open. So, and so this actually works without not just being an R sub n. This works for basically all low minimal vector fields with an isolated singularity at the origin, and under any sort of reasonable assumptions, you get this split in things. And so that's also highly suggestive that this really nice result classification that we have for expansions by trajectories of linear vector fields might not be so far off as that might be very close to the general situation. So that sort of ultimately the state of things right now is trying to see how far we can push the results for trajectories of linear vector fields to, say, trajectories of analytic vector fields near isolated singularities, and so on. And I could go on. There's a whole bunch of results where you could say something like, okay, if I know it's C2 and one of the eigenvalues does this and of the linear part and something else happens, then you can conclude things. It's not my that's not what I want to do right now, is to try to sit around and list all of those things. But there are a lot of tools here that we can use. But at the same time, there are a lot of significant obstacles arising out of we had some obstacles before, possibly arising from transcendental number theory. We got rid of those by just saying, okay, let's axiomatize them away and suppose that we're working over with just suppose that we already have all of the compact trajectories of linear vector fields. And so now we start to run into some more serious difficulties, in that there's plenty of open questions in ODE theory that have been open for a long time, that we kind of would need those answers in order to keep pushing the program further. This can all be wrapped up and made into conjectures, and there's a paper in progress that has this in excruciating detail and care. I don't really want to try to do it in a Blackboard setting like this. But there is further progress we can make along these lines, and then there are some real things where we hit our heads pretty hard. So that's kind of the planar case only, and in the interests of transparency and honesty here, we have to say that once we start going to even polynomial vector fields in 3 space is they're very simple polynomials in 3 space, as such things go, nonlinear ones, that give rise to these chaotic things, the Lorentz attractor, the Rössler attractor. These all come from they're nonlinear polynomials, but barely nonlinear. So we can dispose of them, because we will wind up knowing that they're not the kind of trajectories we want to look at anyway. Those are chaotic. We also know of some other ones we can dispose of, because they're sort of ergodic. They're dense and codense in semi-algebraic sets or something. But there really are we could easily have a whole other lecture on just a bunch of open problems that stand in the way of getting forward here. So the game that relies on ODE theory proceeds by, we hope for situations like this where there is some ODE theory that's known, and that we can transfer to O-minimality, to O-minimal situations. And that will get us a little bit farther. Then there's some other things that are just too far away from us for now. It doesn't stop me from looking, but there are some real obstacles when we have to rely on the ODE theory to answer some of the questions that we want. So in other words, this just to recall, in the case where we were looking at the trajectories of linear vector fields, we used very explicit information from ODE theory to get what I called the tameness half, or the tameness result, the classification of what we wound up with. We needed to understand the trajectories well enough to find out what we wound up with. There was still the other side of that, where there was model theory to be done that helps us understand the other half of the problem, which is understanding what we wind up with in terms of what we started with. That can still proceed in several directions. So I think that's really where I want to start. I really want to stop for today. Yeah, I think I should stop now. And let me just, so ask if there are any questions or comments. And if things are more complicated, you can always just email me and we can have a Zoom or something and we can talk more about this stuff. Sorry, my voice is going. Thanks for your attention.
Thanks, Chris.
Thank you, Chris. I stopped the recording.